as it is in the Matrix. You're in a pod basically, and you're experiencing a world that is, through your senses only. Could you talk about that idea a little bit?
Sure, absolutely. So that idea is an interesting one. I think that the important thing is to talk about whether or not it's really feasible. Now, I know that there are a lot of ways that people can escape from their reality. They can play video games or go to movies, and there's a concept in virtual reality called immersion, or level of immersion, which has to do with how immersed you are in that reality. Mm-hmm. And there are some things that some sort of alternative reality experiences where you're not that well immersed. So you go to a movie theater, you can get engrossed in the show. If something jumps out on the screen or makes a loud noise, you're going to jump out of your seat perhaps. And the reason you do that is because you've gotten engrossed in the show and you're somewhat immersed in the experience. However, it's easy to look around you and see that there's other people watching it. You have peripheral vision. You're not really getting all of the sensory experiences of what's going on the screen. You're sitting in a chair. So that it's really kind of a partial immersion experience. And you can imagine how we can take steps toward a fuller immersion experience with things like virtual reality goggles that have high-resolution screens, or some haptic devices, gloves, and things like that mm-hmm. People have been experimenting with for 10 years at least.
Right.
So the concepts are there of creating simulations that we can experience. And the question is, at what point would we actually be able to kind of get into a scenario where we're in a reality that's kind of indistinguishable from what we think is true reality. And for that, you can start to look at Moore's law. And Moore's law, everybody's familiar with, is the idea that technology more or less doubles every 2 years.
Right.
And it really kind of depends on what you're talking about. For things like transistor density on a chip, it's every 2 years. Processor speed, turns out it's every 2.8 years, and screen resolutions is maybe every 4 years.
Mm-hmm.
And so if you kind of look at where we are in terms of computer gaming, it's an interesting place that we're in. So, for example, if you turn the clock back 25 years or so, there was a game called Pac-Man that used 64 pixel characters, and it was a 64 kilobit screen, ran on a 3 megahertz Z80 microprocessor. And if you remember that game, if you've ever played even the simulations of the game,
right.
There's no mistaking anything in that game for reality. The little fruits that the Pac-Man went around and gobbled up did not look like real fruit. However, if you walk into a electronic superstore today and take a glance at a screen, you'll see a football or a soccer game on there, and you won't be able to tell necessarily the difference between whether it's a live game or whether it's a game like Madden NFL 08. Some of these games that run on the consoles, PS3 and Wii and some of the other consoles, they are so realistic looking that it's hard to tell until you get up close and look a little bit closer.
Yeah.
And the reason for that, of course, is Moore's law. They're running on a machine that's running 2 teraflops. A gigabyte of memory, 8 megabyte screens. So over 25 years, the resolution of screens has increased by 128. Processing speed's gone up by a factor of 1 million, and the resolution of the models of objects in these games has gone up by a factor of 1,000.
Right.
So given that, you ask the question, at what point will we get to the point when it will be indistinguishable from reality? Will it kind of hit the limitations of our perceptual resolution? And it turns out that perceptual resolution for vision is about 150 megabytes, and it's only going to take 16 more years, assuming that we maintain the Moore's law doubling effect that we have been maintaining relentlessly for the past 40 years.
So Jim, that means that someone has actually kind of narrowed it down in regards to the human eye and what the brain can perceive in regards to gigabytes, or what?
Yeah, absolutely. I mean, there's 130 million receptors in your retina. There's about 1 million axons that carry that information through the optic nerve, and then deeper into the brain and the visual cortex, they estimate that there's, again, 150 million or so cells. The 150 million megabytes that I came up with, I just, came up with by looking up the visual acuity of the human eye, at how you can determine angles, and then basically extrapolating that into a large field and knowing how well we can discern colors and understanding how many bits it takes to discern that many colors, you come up with that kind of number. So it's really 16, 20 years or so where we can generate these kind of simulations. And now that's only part of the problem. That allows you to, again, generate a simulation, but how do you get that sort of injected into your senses?
Right.
And that's a different question. The idea of using screens and haptic devices is really kind of clumsy if you think about it. I can't imagine that anybody's going to be fooled into thinking they're in a different reality because they're wearing goggles. You might not realize it for a while, but you can still tell the difference.
Exactly, and I guess also it depends a little bit on how we would get immersed in the simulation, so to speak. If it is all that we have ever known, it would obviously be more difficult to determine that we're in one, right? Exactly.
Now there's some really interesting things going on in the world of nanotechnology that directly relate to your question. So, for example, a couple of years ago, there were some research teams at MIT and Caltech that were able to take monkeys. They had electrodes in their brains, and they showed these monkeys various images. And just by reading the signals emanating from their brains, they were able to tell to an accuracy of 80% what image the monkeys were looking at.
Mm-hmm.
So what that tells you is that even though this is sort of a very nascent, technology, something that we're just beginning to explore, it does show that it's possible to read brainwave patterns and determine what your sensory stimuli are.
Mm-hmm.
In the other direction, there's been a lot done with artificial vision, retinal implants, and things like that. And some devices have been made that have a small number of pixels, 60 pixels, I think, is what they're up to now. But they can feed signals from little cameras mounted on a goggle device into an implant in your retina, and blind people can actually start to see patterns, grids of light.
Right.
It's very rudimentary at this point, but it shows that we're able to feed sensory information directly into the brain because the optic nerve really is an extension of the brain. There are other experiments that are being done that go further back into the brain, into an area, I forget what it's called, escapes me at the moment. The LGN, lateral geniculate nucleus, and I don't know if I even pronounced that right. But,
right.
It's a part of the brain that relays the signals from the optic nerve to the visual cortex, and they're finding that they can stimulate that area and generate, patterns of light that are perceived by the subject. So, so we're getting, we're at the beginning of these technologies, and I think that again you can apply Moore's law, and you can apply. In fact, Moore's law, the pace of technology is even faster at the beginning of technology. So, for example, it took 16 years to develop that 16-pixel version of the retinal implant. It only took 4 years to develop a 60-pixel one, because we're on a very steep part of that curve.
Yeah.
So, what all this says is that it's very likely at some point that there will be either retinal implants or implants deeper into your brain that can intercept your sensory signals and process them, perhaps. So